Thank you very much for inviting me here. It's nice to be here. Thanks for coming. And right, so basically maybe the starting point for the talk is the following very generally and innocently looking question. When is a closed Riemannian manifold close to a lower dimensional object? Of course, in the spirit of this conference, one could ask this question also for metric spaces, and we are going to do it later. All right? And so there are essentially two ways. I mean, what do I mean by this question? There are two ways to measure the distance to a lower dimensional object, and one of these distances uses so-called widths. So assume, for example, that Y is a submanifold or a compact subset of a Banach space. And width is the infimum of S such that there exists a continuous map from Y to a k-dimensional polyhedron, so that for each point the distance between Y and its image is at most S. And there is some kind of more abstract notion of width called Eurozone K width. So there Y is not a subspace of anything. So we take the infimum of S such that there exists a continuous map to some k-dimensional complex, so that diameters of inverse images of all points are bounded by S. Now, if Y again sits in B, it's kind of immediately clear that we could majorize this k-dimensional Eurozone width in terms of width in this Banach space B by less than or equal than 2WKB. And so, if we don't like that UW looks so abstract, I would like to mention that Gromov demonstrated that if we will consider the standard Kuratowski embedding of Y in the space of L infinity function of Y, then it turns out that we are going to have the equality here. So the Eurozone width is just 2 times the width of this embedding into L infinity. So, yes, and since before continuing, I would like just to say a couple of words. In the last part of this talk, there will be also part 2. In part 2, we will be measuring distances between manifolds and the lower dimensional objects in terms of some kind of filling invariance, some kind of isoperimetric type invariance, but I'm going to talk about it later during this talk. So returning to widths, kind of a basic conjecture posed by Gromov and proven a number of years afterwards, like maybe something like 20 years afterwards by Larry Goose, was the following, that if Mn is a closed Riemannian manifold, then Eurozone width could be, and n minus 1 dimensional Eurozone width is less or equal than constant n volume of M to the power 1 over n. And there is the next installment, I mean the next theorem, which was first conjectured by Larry Goose. So after proving this theorem, Larry Goose became interested in the following question. So, okay, so in the previous theorem, we have some n-dimensional manifold. We would like to ensure that it's close to something n minus 1 dimensional. But what happens if we really would like to figure out whether or not it's close to something much lower dimensional, like n minus 2, n minus 3, n minus 4. And then, of course, we cannot use the volume anymore, because it's kind of natural. If something has small volume, it perhaps is close to something lower dimensional, but we really cannot quantify the dimension. So he came up with the idea of using Hausdorff constants for these purposes, and he asked whether or not it's true that if we have a manifold, and maybe even a metric space, we could estimate the distance to some m minus 1 dimensional object in terms of Hausdorff constant. I'm going to tell what is Hausdorff constant in a little bit later and its properties. And it turns out that, yes, that's true, and we proved it jointly with Evgeny, Boris Lishak, and Regina Rotman. So now I would like to remind you what is the Hausdorff constant. So Hausdorff constant, as anyone saw perhaps in some analysis course, it usually appears in the course of defining Hausdorff measures. So Hausdorff, m-dimensional Hausdorff content is infimum over all coverings of X by metric balls B with radius with radii Ri of the quantity Ri to the power m. So here m has nothing to do with X. It's not its dimension, it's just a number. Now practically when m is more than greater than the Hausdorff dimension of X, then we are going to get 0, right? But it makes, unlike Hausdorff measure, this quantity makes sense when m is less than Hausdorff dimension of X. So what are the major differences with Hausdorff measure? The major difference is that we don't require Ri to be small, like in the definition of Hausdorff measure. And the second difference is that we don't normalize by the volume of the unit ball in this definition. So it kind of scaled somewhat differently from, I mean, if we adopt this definition, we of course could have scaled, but we don't want to. So here are some properties of Hausdorff content in order to appreciate that. Essentially, it's monotone, it's semi-additive, it behaves nicely under Lipschitz maps like a measure, like some kind of m-dimensional measure. Now another property. So for example, A is a bounded and connected subset of a Banach space of any dimension, but its Hausdorff content, say with the number 1, will be just equal to its radii, because it's always, in dimension 1, it always, not exactly beneficial, but it doesn't harm to merge overlapping balls that are used to cover A. Now, the next property is very easy, but maybe not immediately obvious. If we will consider linearized quantities HCm to the power 1 over m, we are getting a decreasing function of m, which immediately follows from the Minkowski inequality. And so here is a comparison with Hausdorff measure. So because it scales differently, and because when we define Hausdorff content, we don't impose so many restrictions on the radii of the balls, they don't need to be small, we have this inequality, and we see that if we take linearized quantity HCm to the power 1 over m and compare it with Hausdorff measure to the power 1 over m, they will be different by a factor square root of m. Now, if we apply those definitions to domains of Rn, and if m here is equal to this n, then essentially Hausdorff content up to rescaling is the same as the volume or Hausdorff measure of the set. Essentially because we could take larger balls and subdivide it into smaller balls without any harm. Now, what is the main difference of HCm and Hausdorff measure is that HCm is very much non-additive. It's especially, it's more kind of immediately clear in dimension 1 when we have HC1, because as I just said, HC1 behaves essentially like a radius or diameter, and everyone knows that diameter is very much non-additive. But in fact, it will be true in all dimensions. So consider, for example, two-dimensional disk of radius 1 of very large negative curvature. So it's by definition, since it's disk of radius 1, it's kind of clear that the optimal way to cover it by balls is just to cover it by one ball of radius 1, and its Hausdorff, two-dimensional Hausdorff content is 1, right? Now assume that we will kind of cut out a very small disk from the center of this disk of radius 1. It's a perfunctory examination shows that actually two-dimensional Hausdorff content doesn't decrease. Still, the most optimal way to cover will be by one disk of radius 1. And then if we will just take something small outside of the disk, then HC2 will go even up. So very important to realize that HC is not additive, which of course is kind of problem when one tries to prove theorems about it sometimes, but not that serious problem. So now, soon after Evgeny, Boris, Leshak, me, and Rina proved this theorem, Panas Papasoglu reproved the same result, that the Eurison m-1 dimensional Eurison width is less or equal than C of m HCm1 to the power 1 over m using a different and much simpler method. So far, I mean, methods used by Gromov, and then there is a famous simplification of Gromov's proof by Stefan Wenger, and then Larry Goose, and then us, they used more or less the same general strategy with some variations and some tricks. But Panna's method was completely and totally different, much easier. And as I kind of noticed reading Panna's paper, that if one, in his paper, Pannas didn't care about this constant C of m. But it was clear that his method, even as is, gives better bounds than all more complicated proofs used so far in this area. And I kind of, reading this paper, I noticed that fine-tuning Panna's paper, changing some small here and there, one could come with a very nicely looking constant in this theorem. Urisohn width n minus 1 is at most 8n times Hausdorff constant to the power 1 over n. Now, as we just noticed, that if we care not about Hausdorff constant but Hausdorff measure, we are supposed to multiply by extra square root of n times some constant, and we come up with such an estimate. But also I noticed that if one properly applies Panna's method to manifolds, one gets somewhat better bound, where here, I mean, the optimal bound behaves like asymptotically, like 2 divided by e times n, actually better than n, but I replaced it by this nicely looking estimate where we have just n. Urisohn width n minus 1 of mn is less or equal than n times volume to the power 1 over n. Now it seems like some kind of end of the story, but in fact it isn't. And let me explain why it is not. And in order to explain that, I would like to talk a little bit about applications to systolic geometry, which starts from famous theorem by Gromov that says that if Mn is a closed essential manifold, then the length of the shortest non-contractible closed curve of Mn, denoted by cis of Mn and called systole, does not exceed the volume to the power 1 over n times dimensional constant. So what are essential manifolds? So it's a certain class of manifolds. So essentiality is a property of homotopy types of manifolds. It's not a metric property. So, and it's a class of smooth manifolds that includes non-simply connected surfaces, projective spaces, tori, more general, all spherical manifolds. And if you care about the definition, it's kind of easier to give a definition of which manifold is not essential. A manifold is not essential if there exists a map to a lower dimensional simplicial complex that induces an isomorphism of the fundamental group. Correspondingly, if it is essential if there is no such map. And if we believe in what was said above, the proof of this theorem by Gromov could be done like that. So let me observe here is the crucial connection between systolic geometry and widths, including Urisohn widths. Gromov observed that systole, if Mn is closed essential manifold, systole doesn't exceed 3 times Urisohn width n minus 1 of Mn. And we know from already mentioned result of Guth, this Urisohn width can be measured by constant volume to the power 1 over n. It's not how it was initially proven, but having built up above, we know that once we know how to estimate your n minus 1 dimensional Urisohn width, then in the situation when M essential, we have immediate bound for systole. So let me maybe spend a little bit of time explaining why this is so. So what I'm going to explain, how to prove, I'm going to sketch why systole is at most 3 and in fact 2. So I'm going to sketch why systole for essential manifolds is at most 2 times Urisohn width if this manifold is essential. So basically here is the sketch of the argument. It's not the original Gromov sketch, it's different. So to see that systole is, so basically I'm trying to do it in counterpositive. I am assuming the opposite inequality and I am proving that Mn is not essential. How to do that? So let's start from the definition of Urisohn width. Definition of this series on width guarantees us a map from Mn to some n minus 1 dimensional complex C, so the diameters of inverse images of all points will be less than or equal than half of systole under our assumption. Now we could consider a very fine covering of Cn minus 1 by open sets with multiplicity n. It's n minus 1 dimensional, so that's such a covering exists. So consider connected components of open sets F inverse of those sets Ui. They will cover Mn and have diameters less than 1/2 of systoles. So here we got some covering of our Mn by sets, connected sets Vi, and they have the following property. So they have the property, since here we are using the definition of systole, we know that each closed curve gamma contained in Vi must be contractible in Mn. So such coverings are called inessential. So we got an inessential open covering of multiplicity less or equal than n. Now, a formal way to complete this proof, which I'm not going to take, would be just to invoke some old and not too difficult theorem buried in some very long paper by Albert Schwarz, proven in 50s, about something like vibration and genus. I forgot the name of this paper. It's a very quoted and well-known paper, but what I am referring to is a particular case of some theorem that appears in chapter 14, which is kind of extremely difficult to discover, to read, to understand how exactly it was proven. And it was actually, it was an observation by Roman Karasyov that this theorem kind of immediately applies to systolic geometry. And but let me explain why actually this theorem works. So, it's actually a very simple matter, so I don't want to refer to some theorem. So, and basically what I'm supposed to explain? I am supposed to explain that given an essential covering of manifold and multiplicity less or equal than n, there is some map from Mn to Kn minus 1 that induces isomorphism of fundamental groups. And it's actually a rather simple matter. So basically we proceed as follows. We have Mn, we have its universal covering, and we could lift all those sets Vj to the universal covering. So those Vj live here, and we lift them to some Vj tilde. We would like to leave them to some sets Vj tilde, right? But each set Vj, it lifts into a collection of disjoint open sets indexed by elements of the fundamental group. It is precisely here where the fact that all closed curves in Vi are contractible becomes useful, because if they intersect, we will easily get a contradiction to this assumption. And the rest is easy. We take the nerve of this covering. So here we have this covering, and we take the nerve of this covering, and we have a map to the nerve. M tilde is going to be mapped to the nerve of the covering. And then the nerve will be at most n minus 1 dimensional. So it follows from the fact that our covering has multiplicity at most n. It's inherited this dimension from this complex Cn minus 1 that we used before. We have free action of pi 1, and it remains to check a couple of things. So our complex where we're mapping will be n tilde quotient pi 1 of Mn, but we need to first check that it's a monomorphism of fundamental groups, which is very easy. If you just look how curves become when they are closed or not closed under lifting to its universal cover. And then there is some minor work required to prove that n tilde is indeed simply connected. So basically that's the story. And the upshot of all that is that if we care about non-contractible curves in Riemannian manifolds, so more general spaces, and we would like to do some kind of systolic geometry, study the geometry when our manifold have some topological properties like essentiality or some similar properties, what we really need to be able to find bounds for Eurison widths. In this case, Eurison widths n minus 1. Yes?
So what is the conclusion that we get the map from the universal cover to the nerve?
So we get a map from the universal cover to the nerve of this covering. So this nerve is denoted by n tilde. It's very easy to check that when we kind of go down, when we map M to quotient of this nerve by the free action of the fundamental group, right? So it induces monomorphism of fundamental groups. It's almost immediate. And then we have two choices: some argument of some non-zero lengths, like maybe several sentence lengths, to prove that n tilde is simply connected, which kind of proves everything. But if one is lazy, one could just kill the alleged fundamental group of n tilde by, I mean, there is known, but assume that we don't know it. We just add two-dimensional disks that will kill it in equivariant way, and we just take this quotient for this new complex that's definitely simply connected.
And this contradicts essentiality.
And this contradicts essentiality. So I'm proving counterpositive. I'm assuming that the systole is greater than z, all right? And yes, that contradicts the essentiality. So I assume that there exists an inessential covering, and I prove that if there is an essential cover of multiplicity at most n, the manifold is not essential. That's how it works. I mean, there is an alternative way, it's classical Gromov way that induces Nabutovsky embedding and gives slightly worse constant. Okay, so now I'm going to ask the following question. So what will be the optimal constant in the Gromov's inequality between systoles and volume to the power 1 over n? So Gromov conjectured, so for round projective spaces and some flat tori, the systole behaves like square root of n volume to the power 1 over n, and Gromov conjectured that actually round projective space are optimal. For them, the constant is the largest. Sorry. All right. So, okay, here it is. All right, and and if we really care, I mean, if we don't care about the exact value of the constant, but just about the growth of this dimensional constant as a function of n, we really need to be able to prove the following conjecture, that the Eurison width of Mn is less or equal than constant square root of n volume to the power 1 over n. And basically, one could state even a more general conjecture that Eurison width is less or equal than constant hc to the power 1 over n. By the way, as I mentioned, that even if we forget about rescalings, hc in general is smaller than the volume, just because we are free to use large balls to define them. And the kind of basic examples how Hausdorff content is much smaller than the volume is already mentioned. Disk of radius 1 of very large negative curvature, where the volume is very large when the sectional curvature is very large, and the two-dimensional Hausdorff content is always 1, right? So it would be kind of stronger. But since in this, I mean, the general spirit of this area, that what's true for manifolds typically is true for metric spaces. So we could just conjecture that the following very nice dimensionless inequality, I mean, dimensionless inequalities are very rare. So we could just conjecture that Eurison widths, n minus 1 dimensional Eurison widths for each metric space is measured by dimensionless constant hcn to the power 1 over n, where n has nothing to do with dimension or anything, it's just a number. But of course, we have no clue whether or not these conjectures are true. There is another slightly more awkward technical conjecture that also would help to establish optimal dimensional constants in the Gromov systolic inequality. So if we could embed Mn to the L infinity of Mn, and then to approximate it by Lipschitz map to a finite dimensional L infinity space. So if we will do that, then we see that if, for example, we are able to prove the inequality for the widths in this L infinity of n, with constant square root of n involving Hausdorff measure with respect to L infinity n of mn to the power 1. And we also get optimal constant in Gromov systolic inequality. And here is the first of our, or rather first two of main results in this talk.
On the previous inequalities, capital N dimension of the pattern?
Yes, so capital N, so here we had, I mean, when we do this Kuratowski embedding, we get something infinite dimensional. Some people kind of are averse to infinite dimensional spaces. What I just observed is that we could always sacrificing maybe some 1 plus epsilon by Lipschitz constant embedded into a finite dimensional approximation, which was explicitly done in the very first paper Larry Guth wrote in his career. What? Yes, and now, right, and then it would be just sufficient for us, forget about those abstract Uruson-Witz, it would be able just to approximate Mn to some n minus 1 dimensional complex in this same space, so that the distance between points wouldn't exceed this quantity, but I also don't know how to do that. Right, and now, having said that, now a kind of, I don't know, maybe it would make sense for some of you, it may make sense for me, that maybe one would like to find some width-volume inequalities between width and volume, where the dependence on the dimension is sublinear. It's not what exactly we want, we need something concrete, but since we cannot have something concrete, let's see what we can get. So, right, so once again, if we have Mn that sits in some Euclidean space of dimension capital N, and here you should think about this capital N to be, I mean, there are no restrictions on N and capital N, but kind of our philosophy, we really would like our theorems to work for arbitrarily large capital N. And W, L infinity n minus 1 Mn, is at width with respect to L infinity metric in the ambient of Rn. We just decide to consider Rn as actually n-dimensional L infinity and calculate the width with respect to this distance. And here is the first of results, kind of new results of this talk. It's a joint result with Sergei Vakumov. And it asserts that for a polyhedron Mn, so think some kind of union of submanifolds in Rn, this L infinity width of Mn is less equal than some constant square root of n volume to the power 1 over n. I mean, everything as we want, only instead of this Hausdorff measure with respect to L infinity, we have volume. Now, what's the difference between Hausdorff measure with respect to L infinity and volume? So when we can calculate Hausdorff measure with respect to L infinity, we cover our set by small cubes. Here, we are covering them by much smaller balls. So instead of covering them by cubes, we are allowed to cover them by balls. Balls or cube give exactly the same contribution to Hausdorff measure. But of course, cubes are larger and it's much easier to cover by cubes than by balls. And therefore, right-hand side in our inequality is much larger a priori. Maybe up to a factor which is square root of this very large n than the desired inequality where I have Hausdorff measure with respect to L infinity. But still, that's what we have. Another result. So if we find ourselves in dimension 1 case, so we have n plus 1 dimensional space, we have Mn, and we really would like somehow to map Mn to some nearby n minus 1 dimensional polyhedron, so codimension 2, polyhedron of codimension 2, then we have a dimensionless upper bound for this volume of L infinity. So these two are different theorems with completely different proofs, and I'm going to talk only about the proof of the first theorem without restrictions on codimension. And now let me, because of the philosophy, because of all those connections between widths and symplectic geometry, there are some implications of those results for systolic geometry. And here is what we get. So from this type of inequality. So assume that Mn in Rn be an essential manifold. Then there exists a closed non-contractible curve on Mn, like systole. But now, instead of bounding its length, we are able to bound, so here is maybe our manifold, that sits in some ambient space Rn, and this is our Mn, and we find here some non-contractible curve, and instead of bounding at length, we do something different. We are looking for a cube in the ambient space of small side lengths that would contain our curve inside. It's of course worse than length, but that's what we get. So, and we see that we have here that side length of this cube is const square root of n. Observe that we are allowed essentially in these inequalities to use only the dimension of the manifold, not the dimension of the ambient space. We don't really want to use the dimension of the ambient space. It's taboo for us. So here we have constant square root of n volume to the power 1 over n. In codimension 1, we could do even better. It's just 4 times volume to the power 1 over n. The part B might look a little bit strange. So first of all, where this theorem applies. So the smoothness here is not very important. So we could apply this theorem to say C1 smooth manifolds. And there is Nash-Kuiper theorem that enables us to embed all manifolds that could be topologically embedded to Rn plus 1. They could be C1 asymmetrically embedded as well. So in particular, we could just take flat tori, which corresponds to constant square root of n in Gromov systolic inequality, and embed them in C1 fashion into Rn plus 1. And now we see that part B of this theorem will provide the bound for the length, for the side length of the cube, which will be equal like its square root of n better than the length of the curve. So it might look strange on the first glance, but then if you ever saw all those pictures of tori embedded into Rn plus 1 using Nash-Kuiper theorem, they all look very, very crumpled. And in fact, there is even a theorem by Subhash-Hot and Asaf Naor to this effect that asserts that for many flat tori, all embeddings to all Euclidean space and even Hilbert space have distortion at least square root of n. So there is no apparent contradiction here. So now let me sketch what is the idea behind the proof of yes?
So for part A of the theorem, does that not follow from the systolic inequality that I must be missing something?
Sorry?
So
what exactly is not follow?
The shortest non-contractible curve is the length of the curve is already less than constant times the.
No, for flat tori, we know that assuming volume 1, we know that the length of a systole behaves like square root of n. For flat tori, I mean, for flat tori, we know that there are some flat tori for which it's square root of n. We know that we could embed them asymmetrically, so the length in the embedded tori still will be square root of n. Yet, according to this theorem, it could be embedded into a cube with side lengths equal to 4. Part A? Well, if we knew Gromov systolic inequality, assume that we would knew Gromov systolic inequality with the optimal constant square root of n, then of course it would be weaker than that. But since we don't know it, we don't know, I mean, ideally we wanted to measurize the length of systole, but we don't know how, so we take what we can. So let me sketch the proof of part A. Part B is proven using completely different idea. So the idea in part A is the following. So assume that here we have maybe some. So assume, for example, that we for simplicity, we are in R3. And we have some maybe two-dimensional surface in R3. And we really would like to map it to some one-dimensional complex, so that each point doesn't go too far. So here is the idea. Maybe we would like to map it to one skeleton of the cubic grid. So this will be our, we really would like to find the one skeleton of some cubic grid and to map our M to this one skeleton of cubic grid. So how it could be done? We could consider the dual cubic grid. So assume that we have a d-dual cubic grid, and assume that M2 intersection with this dual, with the one skeleton of the dual cubic grid is equal to the empty space. Then somehow if we have, so here, if we have here this cubic grid and our M doesn't intersect this cubic grid, we could kind of push it out to the one skeleton of the dual cubic grid. Now, why it will not intersect M, we don't know. Probably it will, but maybe we could consider all kinds of translation. And then maybe, if we're really adventurous, we also could consider all kinds of rotations and to find some cubic grid that doesn't intersect our M. And then we will project to the dual cubic grid. And here, if we will do the calculation, and a way of doing calculation is the principal kinematic formula by Santala, Bляшко, and Federer, which applies to curvature measures, but it also applies, in particular, it applies to volumes. So basically, how it can be applied, if we have some kind of if we have a couple of manifolds, and we take one of those manifolds and apply all isometries of the ambient Rn, and we really would like to average the measure of intersection, essentially it's given by product of measures of those manifolds and some dimensional constant. And applying this formula to this story, we see that in order for our plan to work, this cubic grid, those cubic grids shouldn't have length 1. They should have length n, which behaves a little bit like n divided by square root of n. Moreover, we will encounter the following difficulty while doing that. If we will take this, say, square or cube, which will have L infinity diameter 1, and will rotate it, we will increase in this plane picture its L infinity diameter by factor of square root of 2, but in general by square root of n. So if we will apply this idea, we are going to get square root of the capital N from here, and another square root of capital N from here, and we are going to get constant which depends on the ambient, or in the dimension of the ambient space, so it's not going to work for us for two different reasons. It turns out, however, there is a remedy. So, right, so here I listed the problems why this will not work, but here is a new plan. So the new plan is the following. So first of all, this way to so we started from this cubic grid because somehow it provides some kind of nice way to divide our space Rn into cubes into sets of L infinity diameter 1 or L over 2, something like that. This is, however, is not the most efficient. We really would like to find some form, something of codimension 1, so that the complement, connected components of the complement Rn minus Fn minus 1 have L infinity diameter less or equal than 1. But what is important, we really would like to minimize the n minus 1 dimensional area per cell. So if we are using cubes, what will be the n minus 1 dimensional area per cell? Assume that we are talking about unit cubes. We are having 2n faces. So the area per one unit cell in n minus 1 skeleton of the cubic grid will be 2n. If we will take, for example, a sphere, so the ratio of volume n minus 1 of the sphere of radius 1 to the n-dimensional n-dimensional volume of the ball of radius 1 will be also of the order of magnitude of n. However, it turns out, so our first discovery is that there is a more economical periodic form where this ratio is about approximately square root of n. So those forms were first, well, I will give proper reference a little bit later. Now, after we are going to find such forms, so here we are going to find some such forms, they will be capital N minus 1 dimensional, and we are going to have some analog of the skeleton of high and higher dimensions. So we need to build skeleton of high and higher dimension. And finally, we need to prove an analog of the kinematic formula where we average with respect to isometries of L infinity n instead of isometries of Rn, because L infinity is the metric that we care about. So let's explain how to do it step by step. So first of all, where we are going to get the minimal periodic n minus 1 dimensional forms. They are first constructed by Kindler, O'Donnell, Rao, and Wigderson, all computer scientists, because of needs of computer science. A kind of later, much easier proof or construction was done by both Clark and Nog and Noga alone. Then there is another construction due to Asaf, Naor, and Regev. So those first forms, the cells here are not convex bodies, and in Naor and Regev, they get convex bodies and tiling by copies of some convex body, but with worse than square root of n estimate, which is not adequate for our purposes, all right? And so this form divides Rn into domains of L infinity diameter less than 1, and the n minus 1 dimensional volume per unit cube is square root of n.
So is that, if you try to get them with complex domains, do you lose the...
I mean, there is a paper by Asaf, Naor, and Regev, where they lose power of the logarithm, and according to them, they really don't know whether or not it's unavoidable. At least the method doesn't seem to help to get rid of this power of the logarithm. And all this was mostly popular through computer science. So for example, I mean, we had some lecture by Mark Braverman, computer scientists, some honorary lecture, and essentially all of them were devoted by those minimal forms and their applications in computer science. But I'm digressing. So L infinity kinematic inequality. So in the the classical kinematic formula implies that if we have Tn minus 1 in Rn, T is not a torus, it's just something n minus 1 dimensional and Zn periodic, and its n minus 1 dimensional volume in each unit cube is V, and we have a compact m dimensional polyhedron, then the average over all rotations and translations in the unit cube of the minus 1 dimensional volume will be given by the formula. So here is what is important. Here is V times volume times square root of m divided by n. So here this scary dimension capital N will be in the denominator, and that's very good for us, but that's not L infinity kinematic inequality. We really would like to do something like that for L infinity kinematic inequality. So what are isometries of L infinity? Of course, translations, but then also permutations of coordinates, and all permutations of coordinates, and also we could always replace xi by minus xi. So if we forget about translations, the rest of the group is a group with 2 to the power n factorial transformations that are sometimes called sign permutations. Permutations plus choice of signs of each element. And that's where we are going to average. And what we proved with Sergei, in our paper with Sergei, there is the following L infinity kinematic inequality for all z to the power n periodic Tn minus 1, the average m minus 1 volume of intersection of something m dimensional, where m is anything, with s Tn minus 1 plus a, where s is the signed permutation and a is the translation, will be bounded above. So here we have a discrete set of transformations. We don't hope for equality like an honest kinematic formula. We hope for inequality. And in fact, the constant in our inequality is slightly worse than the constant in the kinematic formula, but has the same order of magnitude. It's square root of m divided by n. That's kind of what's important for us. Now, observe that when the number v behaves like square root of n, and that's precisely our case. In our form, v behaves like square root of n. This square root of n nicely cancels with square root of n in the denominator, and the average of n minus 1 volume of the intersection is square root of m volume m to the power square root of m volume of m-dimensional volume of our m. Okay, so here is our idea. Now we are going to start from this form and start defining its skeleton of high and higher dimension. How do we do that? We intersect it, we take this form, one copy of this form, the second copy. For the second copy, we do random translation in cube with side length 1 and random signed permutation. It's not invariant with respect to the signed permutation, so we need to do that. And we have an upper bound for the intersection. That intersection will be for us like a skeleton of codimension 1. Then we do it again and again. And after m steps, we will obtain, I'm not sure why it's Sn. It's not Sn, it's Zn, periodic. Sn means Zn periodic. Fn minus 1, and we could kind of calculate this volume a little bit carefully. The exact upper bound that will come from bounds for the area of the form that I didn't tell you about will look like 2 pi to the power m square root of n factorial divided by n minus m factorial. And of course that's bad, because what we have here, it behaves roughly like square root of this large capital N to the power m. But so this will play the role of n minus m skeleton. And where exactly? So in our initial construction, we had kind of one cubic grid. Its skeleton didn't intersect our set, but then there was a dual grid, a dual skeleton, where we were pushing our manifolds. The role of dual skeleton will be played by the nerve of the open cover of the complement. Here we have a lot of copies of this form. Here we have those open sets together, and we have several copies of these forms. Together, the nerve of this covering will be m minus 1 dimensional. And to this m minus 1 dimensional skeleton, we will be pushing our manifold, providing that it doesn't have that its intersection with this form n minus m. So we have our manifold of dimension m. We take this form n minus m dimension, kind of after we take signed permutation, translations, and we hope that after we do that, the number of points of intersection will be 0. And then we will be, if so, we will map f to this dual skeleton. And it remains to use one more L-infinity kinematic inequality. So here we are using it in the situation when we intersect something m-dimensional and n minus m-dimensional, and the dimensional constant will be exactly what we want, 1 divided by square root of n choose m, which will cancel, almost cancel. So here we have square root of n factorial n minus m factorial in the volume of n minus m, and it will be nicely cancelled with this square root, but of course we will be left with the square root of m factorial, right? And this square root, so essentially we will be left with square root of m factorial. We are supposed then to take 1 to the power, power 1 to the power m, and we are going to get square root of m as advertised. So that's the sketch of proof. And now we have 11 more minutes, and I'm going to briefly explain the other side of this story when we kind of try to evaluate distance from a manifold on lower dimensional object in terms of the volumes of the fillings. Everything starts from rather famous isoperimetric inequality of Gromov in Banach spaces. So basically, it says that given Mn in some Banach space, finite to infinite dimension, we are able to fill it by something, by some pseudo-manifold of volume bounded like in the isoperimetric inequality. And in fact, what really Gromov cared about, he really cared about the maximal distance from the point in this filling to B. He called this maximal distance filling radius. And what was important that this distance is at most volume to the power 1 over n times const. And in fact, it's essentially follows from this is some kind of minimal objects, and minimal objects satisfy monotonicity. So the second inequality was just consequence of the first, rather easy consequence of the first. And in our paper with Evgeny and Leshak and Rina, we decided somehow, we had the following definition. So let's generalize all this story as follows. So assume that we have a compact, so let be a compact subset. So X is compact subset in B, where B is, for now, is a Banach space. And M is any integer number. M is any positive number, not necessarily integer. M filling of X consists of M is integer, sorry. Now M is integer. Integer positive. And M filling consists of M-dimensional polyhedron and continuous map X to Km as in the definition of the width. But this time, by this time, we really would like to have a homotopy between inclusion of M. So here is M, or X, and here is some K of dimension M, and here is some map phi. And we don't want to merely map. We really would like to have some kind of filling. We would like to have a homotopy between the inclusion of M and composition of M to K and its inclusion to B. And of course, since it's a Banach space, we can always have some homotopy. And now goal to find this homotopy, this M filling, with a good control of the size, volume of Hausdorff content of the image, as well as the width. Yes? Yes, so here, yes, so M and X, so M is equal to X in this story. M, N, and X are the same. Sorry for confusion. So, for example, the result of Larry Goose about width, it was obtained de facto. He didn't use this terminology at all, but de facto he constructed, it was obtained as a part of this theorem. He really, in some L infinity, or even some finite L, which sits in L infinity, he constructed the filling of manifold Mn in accordance with this terminology, so that both widths was bounded in terms of the volume to the power 1 over n, and volume was also bounded, as in the usual isoperimetric inequality. And our result about Eurison widths with Evgeny, Rina, and Leshak also was obtained as a part of much more general statement. So here in this theorem, M is not even integer, and therefore there is this funny ceiling function of M minus 1 for dimension of this complex. So we have a continuous map and homotopy, and in our theorem, it's kind of high codimension isoperimetric inequality for Hausdorff contents instead of the volumes. And as a bonus, we also obtain the upper bound for the width. That's property 1. And that's property 1 really is a conjecture of Larry Guth. And property 2 is isoperimetric inequality for Hausdorff contents. What is interesting about this result? M now has absolutely nothing to do with the dimension of Y. So it doesn't make sense to consider M greater than the dimension of Y because we're going to get just 0. So de facto, M is less than or equal than the Hausdorff dimension of Y, but it could be much less. And as in the Gromov paper, we have here C of M, where M definitely is not the dimension of the ambient space, and even not the dimension of Y. It's M that we used in order to define the Hausdorff content. What's the main difficulty in proving this theorem? So Gromov's theorem and all its further versions, including Larry Goose, are proven using some kind of argument that could be described as cutting of thin fingers. One identifies some area in the manifold or a space that looks like a thin finger, cuts it, replaces it by a minimal surface, getting something of smaller volume, and fills the gap using, for example, the cone inequality. And those fillings together will form this W, this filling that we are looking for. And we can do it again and again and again. And this filling is obtained using some kind of induction assumption. All right. And this filling is obtained by some kind of induction assumption. And as I said, that Hausdorff content is completely, we cannot assume that it's additive. So it's very, very difficult to identify thin fingers. The danger is that when we are talking about Hausdorff content, we could cut out something from our manifold. Its Hausdorff content will not change. Then we add something, it will increase, which would be bad. All right, and more recent result due to this Sergei Avakumov looks almost exactly like the previous theorem with one exception. So in the previous theorem, we were, like in the isoperimetric inequality, we were comparing m plus one dimensional Hausdorff content of the image of the homotopy of the filling with the m dimensional Hausdorff content of y. And here we are comparing, since m has nothing to do with dimension of y, so why I'm supposed to compare two different functionals, m-dimensional functional, m plus one dimensional Hausdorff content? It make more sense to compare the same functional, HCM. And in fact, it can be done, and this result will be actually strictly stronger because, as I mentioned, we have kind of monotonicity. If you take HCM to the power 1 over m, it's a monotonically decreasing function. In particular, the right-hand side in 2 now is greater or equal than the right-hand side in the isoperimetric inequality, so it's a stronger theorem. Now, I am going to spend the remaining 3 minutes, first of all, by briefly explaining how it could be even further generalized, and then explaining what does it mean in the classical codimension 1 case, or finite codimension case. So how to generalize it? Y here is very general. M is very general. Here we apply it to general compact set. So what is not general here? The fact that B is a Banach space. It looks very restrictive in comparison with everything else. So we discovered that, right. And before doing that, here is just one word about the difficulty of this theorem in comparison with the previous one. The main difficulties boil down to the fact that here we cannot use the cone inequality. So cone inequality is very good when you have volume or Hausdorff content of dimension m, and you take cone and you estimate m plus one dimensional Hausdorff content of the cone. Here, when we are using the same dimension, cone inequality just doesn't work. So essentially one needs to reprove previous theorem without any mention of the cone inequality. But after we did that, we immediately got, almost immediately, got generalization for a larger class of B. Now we assume that B is not necessarily Banach space, but a geodesic metric space with a linear contractibility function. Each metric ball of radius r is contractible in concentric metric ball of radius lambda r. And so if B is linearly contractible, the previous theorem holds with some minor restriction. So, and if we are not assuming that B is finite dimensional, if we are not assuming that B is, one of possible applications will be when B is a Riemannian manifold, a Riemannian polyhedron. If we are not assuming it, we need to assume that our set Y is a polyhedron. And there are not that many. For geometry, it's interesting to apply this theorem in the case when B is a closed Riemannian manifold, but of course it's never lambda linearly contractible. It's lambda linearly contractible, yes. So what's another difference of this theorem? We get some powers of lambda that appear on the right-hand side of inequalities. And then we observe that typically, in Riemannian geometry, we have linear contractibility only for small metric balls, for balls less than some R0. And our theorem also will hold in this case, but we need to assume that Hausdorff content of our y is sufficiently small, namely it's measurized by some explicit constant, C of m R0 of m divided by some power of lambda, where the exponent depends on m. So this version of the theorem will be applicable, obviously, for Riemannian manifolds with injectivity radius bounded below, but also for manifolds with sectional curvature bounded below volume and diameter. It's clear that we cannot hope for this theorem to be true for all manifolds, just because high dimensional sets are not always homotopic to lower dimensional. So we need HCM to be small. So for there somewhere here embedded an assertion that we have Riemannian manifold like that, and HCM is small, then the set could be kind of homotoped to something lower dimensional. Forget about all kinds of estimates for this homotopy. And now I would like to compare it with something well known. So in dimension 1, this is a generalization of so-called boxing inequality, which was proven by Gastins and reproven in a different manner by Federer. Gastin was a PhD student of Fleming, who was then a collaborator of Federer. And in 1 year, Federer reproved it using a different method, right? And it's very similar inequality if we have a domain in Euclidean space bounded by something, then HC, n-dimensional HC of this omega n plus 1 is measurized in terms of HCn of the boundary. And it's easy to see that if we don't care about constants, it's strictly stronger than the non-sharp isoperimetric inequality. And in fact, thanks to Vladimir Mazia and Adams, it had a lot of application analysis that were kind of flourishing through 1980s, 1990s, but still there are some papers in this direction that appear. So since we got stronger version of Sobolev inequality, well, one could get, since we got stronger version of isoperimetric inequality, one also gets a stronger version of Sobolev inequalities that involves Jacquet integrals with respect to DHCM. That's defined using essentially Cavalieri principle. And one of those inequalities looks like that. Where is it? Yes, like the inequality at the bottom. We take, here I'm writing the Sobolev inequality, but on the left-hand side, instead of norm, Ln plus 1 over n norm, I'm just taking kind of L1 norm only with respect to DHCn minus 1. And the left-hand side will be a priori larger than the left-hand side in the classical inequality. So it's kind of used in analysis for studying properties of some fine sets in classical analysis in Rn of high codimension. So jointly, our result implies this boxing inequality. Only here m is not n, but any number between 0 and m. And what's important, the constant depends on m. I think it was previously known if I would write this inequality, but this constant would depend on the n, it would be known. The result where c depends on m, I think, is new. And similarly, the last thing that I'm going to say today, that in high codimension, we also have an inequality like Gromov's, where with bound of some analog of filling radius with respect to HCM. And instead of the isoperimetric inequality, we see that HCM of the filling is measurized in terms of HCM of a man. So that's it for today. Thank you very much.